Welcome to Physics 371 Online. I'd like to review the section in the textbook that deals with curvilinear coordinate systems. And it won't come as any surprise to you to know that because of the symmetries of objects or phenomena that we find in the world, sometimes it's more convenient to define non-Cartesian coordinate systems rather than the familiar x, y, and z. The two of greatest significance, at least for this course, are spherical, polar, and cylindrical coordinate systems. So here I'll give an overview of the spherical, polar, or sometimes just shortened to be named the spherical coordinate system, and let you review the cylindrical system in the textbook. So first, just to define the spherical coordinate system, which should be familiar from previous courses, a point in space, instead of being indicated by x, y, and z coordinates, is given by r, theta, and phi. Here's the Cartesian coordinate axis. So imagine a point at the tip of this arrow, a distance r away from the origin, and an angle theta away from the positive z-axis. So the angle drawn from the positive z-axis down to this vector will be theta. Okay, then in order to define the angle phi, which will tell us where this point is with respect to the z-axis and the x and y axes, we drop a perpendicular line down from the point to the xy plane. Then connect that point with the origin. The angle from the positive x-axis to that line that now sits in the xy plane is the angle phi. Theta is sometimes called the polar angle because it's measured from the pole, the z-axis, while phi is called the azimuthal angle. There exist simple trigonometric relationships between r, theta, and phi, and x, y, and z, as you can see by referring to the diagram. Z is simply the projection of this r vector onto the z-axis, which is r cosine theta. The x component then is easy to get because the line that's in the xy plane now has length r sine theta, and the projection of that onto the x-axis gives the x-coordinate. So it's r sine theta times the cosine of phi. And similarly, the projection of that same line of length r sine theta onto the y-axis is r sine theta sine phi. So those are the three simple relationships between the coordinates. In the spherical coordinate system then, the general form of an arbitrary vector, instead of having x, y, and z components, has r, theta, and phi components, so that a general vector A can be written in this form. And one note, although the r hat, theta hat, and phi hat unit vectors are of necessity mutually perpendicular, their directions depend on their position in space. So for example, at the tip of this arrow, the r hat vector will point in a different direction than it would if that point in space were over on the other side of the positive x-axis. And so motion in space changes the orientations of the unit vectors even though they stay mutually perpendicular. One consequence of this is that the derivative of the r hat unit vector with respect to theta, so how does the r hat vector change with respect to theta? That's certainly not zero, because as theta changes, the direction of the r hat vector changes. However, in Cartesian coordinates, it's pretty obvious that the x hat unit vector always points in the same direction, no matter what the y coordinate happens to be. And so this kind of a derivative in Cartesian coordinates is obviously zero, but a similar sort of derivative in spherical coordinates is non-zero. Well, in order to in order to do vector operations in spherical coordinates, we need to be able to write down these expressions, these differential elements that appear in, for example, the three fundamental theorems of vector calculus, dl, dA, and d tau. So the way to do this is to start at a point in space at the tip of an arrow whose end is at the origin, and introduce tiny increments in the three variables r, theta, and phi. So here's the Cartesian coordinate system, and then the point in space at the end of this arrow will now be incremented by a tiny displacement along the r hat direction. So a change in r would be written down as dr. It would have a length dr, and it would point in the r hat unit vector direction, as indicated by the green arrow. All right, so let's imagine doing the same thing, but now for a tiny increment in the angle theta. So here's a new sketch with the original vector in the same place, but now let's imagine that we rotate this vector in a way that increases theta by a tiny amount d theta. Okay, so what is the displacement between the tip, the original tip, and the final tip of the arrow? What would that be? And it's pretty obvious from simple geometry that that's r d theta, because the subtended angle in that triangle is d theta. R is the side, so it's r d theta, and it's in the theta hat direction, as indicated again by the green arrow. We can play this game one more time in the phi direction, but in order to do this, it's more convenient, since the phi angle is with respect to rotation around the z-axis, it's more convenient to drop down into the xy plane this projection of the original vector. And so that projected line has magnitude r sine theta. And we want to look at what happens to this now as we rotate by a tiny angle d phi. So it rotates through a tiny angle d phi. What will be the displacement? Well, it's pretty simple to see that, again, this will form the side of a triangle opposite an angle d phi, where the leg of the triangle is r sine theta. And so that displacement for a positive rotation is r sine theta d phi times phi hat. It's in the phi hat direction. So each of these three results gives us the components of the differential or infinitesimal displacement vector dl. So dl then could be written, if you move from one point in space to a nearby point in space, the most general kind of displacement will have components along all three coordinate directions. So dl will be dr r hat plus r d theta theta hat plus r sine theta d phi phi hat. By analogy to Cartesian coordinates, sometimes people think that this should simply be dr r hat plus d theta theta hat plus d phi phi hat. But spherical coordinates are a little bit more complicated, and it turns out that that's not quite right. So be careful. Don't make that assumption. The volume element d tau, then, in spherical coordinates is simply given by the products of these three components, because if we take those three components and multiply them together, they form the length, width, and height of a tiny box, which defines the volume element. And so d tau is just the product of dr, r d theta, and r sine theta d phi. And we usually write this by collecting the terms, writing it as r squared sine theta dr d theta d phi. And that's certainly something that you should have at hand when you start to work on homework problems. What about the area vector dA? Well, that's always normal to whatever surface is involved in the calculation, and so that's going to depend specifically on what surface is involved. So there's no simple way to write down a general expression for dA. It all depends what kind of surface over which the integral is taking place. So now let's look at putting this information to use in doing an integration of a function in spherical coordinates. Often we want to integrate a function over all space, and so let's show how that's done in spherical coordinates. All we really have to do is remember the volume element d tau and then figure out the correct limits on the variables r, theta, and phi. In Cartesian coordinates, that's really easy. We integrate from minus infinity to infinity along x, y, and z. But for r, theta, and phi, it's a little bit different. So here's the form of the integration. Of course, since there are three variables, this is really a triple integral, as we will make clear in a moment, but often we just write a single integral and put a notation all space to indicate the domain of the integration. Now the limits in the radial direction, if we think about it, have to go from 0 at the origin to infinity. That's not too difficult. But what about phi and theta? Well, phi, representing a rotation around the z-axis, one complete rotation that would then take in contributions throughout all possible values of phi, would go from 0 to 2 pi. Theta is just a little bit more complicated. It's tempting to think that theta should also run from 0 to 2 pi, but if you think about it, the polar angle measured from the positive z-axis, by the time you get down to the negative z-axis, you've only gone through an angular distance of pi. And so that's all you need. That has covered all of the volume that's possible along the polar direction. Okay, so be careful with that, and remember, you may have to go back to a sketch occasionally to see why that works. But this gives now the limits for the integration along r, theta, and phi. So if we wanted to integrate a function f over all space in spherical coordinates, here's what it would look like. d tau has been written in explicitly as r squared sine theta dr d theta d phi. F is in here, and we have the proper limits. So, of course, given some sort of function, one would integrate from the inside out, do the r component first, and then the integration along theta, and the integration along phi. Finally, the review of this section is complete by tabulating the new forms that the gradient, divergence, and the curl have in spherical coordinates. The spherical coordinates are very useful for simplifying various aspects of the problems that we will treat in this course, but one of the prices that we pay is some of the vector operations, some of the derivatives, the gradient, the divergence, and the curl of functions get more complicated in spherical coordinates than they are in Cartesian coordinates. So see the textbook for the derivations. There's especially a very elegant way of getting these results in Appendix A of the textbook. But you'll see the gradient doesn't look too bad, although one sees more than simply the derivatives of a function with respect to r, theta, and phi. One sees a 1 over r term and then a 1 over r sine theta term. So things are a little bit more complicated than you might remember from Cartesian coordinates. And this becomes really obvious when we look at the divergence and when we look at the curl. The curl being a vector operator, giving us a vector as a result, is even more complicated because we have separate r hat, theta hat, and phi hat components. So note that these kinds of the derivatives that you would expect to be present in these expressions are there. But at the same time, there's more complications that arise from factors of r and sine theta that float around in these expressions. Also note, for example, in the divergence, these are the forms that are given in the textbook. It might seem a little bit odd to write this as d by dr of the quantity r squared times the r component of vector v, but that's just for compactness. One could certainly expand that derivative immediately, but then the expression would be a little bit longer because we'd be adding a separate term. So this is the way that these results are tabulated in the textbook. I do not expect you to remember these things from memory, which is why when you take exams, the front inside cover of the textbook will be provided with your exam because it contains these formulas. For completeness, let's also look at the Laplacian, which is del squared of a scalar function. And you can see once again there are various sorts of second derivatives that are either present or are implied. For example, the first term has d by dr of dt dr, and one of the things that will generate is a second derivative. But there are other terms as well, and so we see the same thing for the theta and for the phi hat, the phi components. So this hopefully gives you a quick overview of the material from this section in the textbook, and in class we'll start to work on some problems.